Okay, thanks for joining me for our 5th tutorial. So we're first going to discuss tests and plots for examining bivariate data. We'll talk about differences between parametric and non-parametric methods. And finally, we'll conclude with some midterm tips and practice questions. So far in the course, we've talked about confidence intervals and hypothesis tests when we take a sample of data and want to make statements or statistical inferences about the mean of a population given the information in our sample of data. And so far, we've limited our discussion to the mean of a single population. This isn't really all that useful for real-life applications, but this was more to lay the foundation for understanding tests for more complex data. In the rest of the course, we're going to be talking about relationships and inferences with bivariate data. So bivariate just means inferences when we have two variables. So when analyzing relationships with two variables, we usually designate one as the x variable and one as the y variable. X is the explanatory variable and is used to try to explain or predict the other variable. There are many different names that are used for the x variable, including independent variable, predictor variable, covariate, but the main thing to remember is that this x variable is believed to influence the outcome. The y variable is known as the outcome variable, and this is the variable we're trying to explain or predict. And other terms used to refer to the y variable are dependent variable or response variable. In some cases, we might be interested in the relationship between two variables when there is no natural order between x and y. But generally, we believe that the explanatory variable or x variable has some influence on the outcome or y variable. So methods for analyzing relationships between two variables are generally broken down into two distinct classes of analysis, parametric and non-parametric. The biggest difference between parametric and non-parametric tests is that parametric methods usually assume that the sample data follows a normal distribution, and therefore often requires a large sample size to meet this assumption. Parametric methods rely on parameters, which means that they generally use means and standard deviations, and they make full use of the available data. They use all the numbers and observations available, which is a big strength. And another important strength is that they have higher power than non-parametric methods if the assumptions are met, meaning they are better able to detect a false null hypothesis. So parametric methods are generally preferable to non-parametric methods if the data meets the assumptions. But some weaknesses are that they are sensitive to the effects of outliers and rely on more assumptions than non-parametric methods. On the other hand, non-parametric methods make very few assumptions about the distribution of the variables being analyzed, which is a strength. They do not require that the data be normally distributed. They do not work with means and standard deviations, but instead rank observations in the data from smallest to largest and worked with these ranked data rather than the actual data. This is a weakness because non-parametric methods make less use of the available information in our data by getting rid of the actual data values and working with ranks instead. So they don't use all of the available information. But some strengths of non-parametric methods is that they make basically no assumptions about the distribution of variables, so a large sample size isn't required, and they are less sensitive to outliers and skewness in the data. But in general, parametric tests are preferred and more common as long as your data meets the necessary assumptions. So this is a chart showing the type of parametric and non-parametric tests used depending on the characteristics of your explanatory and outcome variable. For the rest of the course, we'll discuss these tests and how to use them for statistical inference, but this is just an overview to help you get an idea of when you use certain parametric and non-parametric tests. The first question you ask is if the groups are dependent or independent. If the two groups contain totally different people, for example, men versus women, they are most likely independent. If the two groups consist of the exact same people, so for example, before and after scores, then they are most likely dependent. Dependent groups are also sometimes referred to as paired groups. And once you've determined whether the groups you're comparing are dependent or independent, you then determine whether your explanatory and outcome variables are qualitative or quantitative. So I'll quickly review the differences between qualitative and quantitative variables in a second, but there are more details in Module 1 on this as well. But if your explanatory variable is qualitative, you also need to know the number of levels or categories it has in determining which test to use. So for example, let's say you're interested in the association between gender and weight. Gender is a qualitative variable with independent groups, and weight is a quantitative variable. If you're comparing the weight of men versus women, you would use a two-sample t-test, the parametric test, or a Wilcoxon rank sum test, which is the non-parametric test. On the other hand, if you're comparing three gender groups, so let's say men versus women versus non-binary genders, you would use either ANOVA or the Kruskal-Wallis test. So I already went over this in our first tutorial, so I won't spend a lot of time on this, but qualitative variables can be either nominal or ordinal. So nominal qualitative variables have no natural ordering, so for example, gender. Or these can be ordinal, where they have categories with a natural ordering, but the intervals between each interval are not equal. So for example, first, second, and third in a race. Quantitative variables can be discrete, so they can take on a countable value, so for example, the number of people in your class. Or they can be continuous, where they can take on any value, so for example, age of 33.2 years. And in terms of scale of measurement, quantitative variables can be measured on the interval scale, where there are equal intervals between each level, but no absolute zero, so for example, temperature. Or these can be measured on the ratio scale, so there are equal intervals between each level with an absolute zero, so for example, weight or height. And most quantitative data is on the ratio scale. So here's a decision tree to help you decide which test you should use. With this, you first ask whether your explanatory and outcome variables are numeric or categorical. From there, you ask whether or not you're comparing one group, two groups, or three groups. Then asking whether or not the groups are paired or independent, and whether your data meets the assumptions for a parametric test, or you should use the non-parametric test. And this will tell you which type of test you should use. So both this and the other graph show pretty much the same thing, but they're just different ways of helping you decide which test is appropriate to use based on your situation and your variables. So here's a table that shows ways to display data depending on the data and types of variables that you have. So univariate data means you're interested in one variable. So for example, the distribution of weight, whereas bivariate looks at two variables like we've just discussed. So the relationship between weight and height. For qualitative univariate data, you could use bar plots, pie charts, and frequency distributions. And you can also display quantitative variables in lots of different ways. So histograms, box plots, grouped frequency distributions, dot plots, and stem and leaf plots. With bivariate data, if you're looking at the relationship between two qualitative variables, you can use mosaic plots, contingency tables, and side-by-side bar plots. If you're interested in two quantitative variables, you can use a two-way scatter plot. And if you're interested in the relationship between one qualitative and one quantitative variable, you can use side-by-side box plots. If you're curious what any of these types of graphs or displays look like, you can always check out the first tutorial where we went over these, or the Module 1 notes. So now I just want to talk a bit about the format of the midterm. I just want to start out by saying that I have not seen the exam, so I don't know what's on it, but I do know the general types of questions that will be on the exam. And the questions will be similar to those on assignments and the module notes, but of course you won't need to use R for anything. So first of all, there'll be questions about concepts and definitions. So for example, what's a standard error? What's the difference between a sampling distribution and the distribution of the sample? The next type of question are those that will say, given a situation, which graphical plot or test should you use? So this is when you should know when it's appropriate to use certain tests. So for example, when to use the Z-score formula for individuals or samples, or the t-test. If you're asked to do a hypothesis test on the exam, remember to follow all of the steps for hypothesis testing that we discussed in our last tutorial. And the final type of question that you'll be asked about are interpretations. So for example, interpret a 95% confidence interval, test statistic, or p-value. And one thing to remember here is to relate your interpretations to the context of the example. So if you're asked to interpret a p-value of 0.03, you wouldn't just say, given our null hypothesis is true, there's a 3% chance that we would observe the data we did. You have to be very clear about what the null hypothesis is and the values that you're referring to. So for example, given that the blood pressure of coffee drinkers is equal to that of the general population, there's a 3% probability that we would observe the sample mean blood pressure we did of X or more extreme among coffee drinkers merely by chance. And these definitions have to be precise. So in statistics, the values we're interpreting often have very specific definitions. So it's best if you don't try to get too creative with your wording when interpreting these values, because even changing only a word or two can drastically change the definition or meaning. Okay, so now are just a few midterm tips. So of course, review your class notes, tutorial slides, and module notes to make your cheat sheet. And one thing that I find helps is to start with the main ideas or key concepts and then fill in the details. Another thing is to review the practice questions from the module notes, tutorials, and Pagano textbook. And also to review your assignments and try to work through your calculations or think through how you would approach the questions without looking at your answers. And my last tip is about when you're actually writing the exam, and that's to manage your exam time wisely. The time does go pretty fast in these exams, so I would prioritize the questions that are worth the most marks and skip the questions that you're not sure about right away and come back to those. So let's try a practice question. Trying to encourage people to stop driving to campus, the university claims that on average it takes people 30 minutes to find a parking space on campus. A random sample of 25 driving times to campus were taken and a mean of 25 minutes was calculated. Assuming that the time it takes to find a parking spot is normal and that the standard deviation equals 8 minutes, perform a one-sided hypothesis test with an alpha of 0.10. So like I said, whenever you're asked to do a hypothesis test or asked to compare the means or some sort of difference, you should address each of these steps. So first we begin with an assumption and clearly state our null and alternative hypotheses. Since this is a one-sided test, our null hypothesis is that the mean time to find a parking space is equal to 30 minutes, what we assume the mean time to be. Our alternative hypothesis is that the mean time to find a parking space is less than 30 minutes. If this were a two-sided test, our null hypothesis would be the same, but our alternative hypothesis would be that the mean time is not 30 minutes. So it could be above or below 30 minutes. And remember that with hypothesis testing, we're not trying to prove the alternative hypothesis. For example, we're not trying to prove that the mean time to find a parking spot is less than 30 minutes. Instead, we're trying to disprove the null hypothesis that the mean time is equal to 30 minutes. And if we can convince ourselves that the null hypothesis is not true, this provides us with evidence that the alternative hypothesis is likely true. Our second step is to make sure the assumptions for hypothesis testing are met. And so based on the description of the study, we can assume that our sample values are independent, so that each of the 25 driving times are from separate drivers. And we know that this is a random sample. Our sample size is 25, and we know that the data are normal, so this allows the central limit theorem to apply. Our third step is to calculate a test statistic. Since the true population standard deviation is known, we calculate a Z statistic. We assume our true mean to be 30. Our sample mean is 25, our true standard deviation is 8, and our sample size is 25. So we plug this into our formula to calculate a Z statistic of negative 3.13. And this tells us that our observed sample mean is 3.13 standard errors below our hypothesized mean of 30 minutes. Our fourth step is to calculate a p-value or critical value to determine if we should reject or fail to reject our null hypothesis, and either is acceptable. If we want to determine a p-value, we take our score of negative 3.13 and we determine that the p-value for this is 0.0009. This p-value tells us that if we assume that a mean of 30 minutes is correct, so that the null hypothesis is true, we would observe a sample mean of 25 minutes or lower 0.09% of the time. So as I mentioned, we can also calculate a critical value as a way of testing our hypothesis. We determine a critical value by taking our alpha level of 0.10 and find that the associated critical value with a one-sided hypothesis test is negative 1.28. And so what this means is that any z-score below negative 1.28 is in our rejection region, meaning that any z-score below this value will have a p-value smaller than our significance level of 10%. If we had been conducting a two-sided test rather than a one-sided test, our p-value would be 0.009 times 2, which is 0.0018. And our critical value with a two-sided test with a significance level of 10% would be positive or negative 1.65, since this is associated with having 5% of the distribution in each tail. So any z statistic more extreme than 1.65 would be in our rejection region. If you don't understand why this is the case, you might want to review the last tutorial where we used the same question to calculate both a one- and two-sided hypothesis test. Okay, so back to our one-sided hypothesis test at a significance level of 10%. Since our z-score of negative 3.13 is less than our critical value of negative 1.28, or since our p-value for a score of negative 3.13 is 0.0009, and this is lower than our alpha of 10%, we reject the null hypothesis and conclude that we have evidence to believe that the mean time to find a parking space on campus is less than 30 minutes. Here's another question. A study wants to see if there's a relationship between age and blood pressure. The researchers recruit 500 people to be in the study and collect information on age, gender, smoking status, blood pressure at one specific point in time. What type of study is this? What is a limitation of this type of study? How would you summarize age for all participants graphically? And how would you summarize blood pressure according to gender graphically? And finally, how would you graphically display the relationship between age and blood pressure? So we know this is a cross-sectional study. All of these values were measured at a single point in time. And a limitation of this type of study is that temporality cannot be determined. So if we examine the relationship between two variables, we won't know the temporal direction of this association. You could summarize age for all participants graphically using a histogram, although there are others that you could choose. And you could examine or summarize blood pressure according to gender graphically by using a side-by-side box plot. And you could graphically display the relationship between age and blood pressure using a two-way scatter plot. Okay, another practice question. A research group wants to estimate hypertension among men aged 50 to 60 years in Thailand. They randomly and independently selected 150 men in this age group in Bangkok and find a sample mean systolic blood pressure of 110 with a sample standard deviation of 18.6. Construct a 95% confidence interval for the mean. What is the margin of error and how do you decrease the margin of error? So we turn to our confidence interval formula, and since we don't know the true standard deviation, we use a t-statistic rather than a z-statistic to calculate our confidence interval. But that being said, our sample size is quite large with 150 people, so we know that our t-distribution and t-score will approximate the z-score at the same level of significance. So in this case, we are calculating both upper and lower bounds for our confidence interval. Unless you're asked specifically to calculate only an upper or lower bound of a confidence interval, you should always calculate both the upper and lower limits. And this follows the same reasoning why we should always conduct a two-sided test unless we're specifically asked to conduct a one-sided test, which we talked about in the last tutorial. So we first calculate the t-statistic for our two-sided 95% confidence interval. And we can use our Z table here, like I said, because our sample size is large. And so a Z statistic or a T statistic with a large sample associated with 2.5% in each side of the distribution is 1.96. So using our confidence interval formula, we plug in our T value of 1.96, our sample standard deviation of 18.6, and our sample size of 150. We add and subtract this from our sample mean of 110 to get a 95% confidence interval of 107.02 to 112.98. So now we interpret our 95% confidence interval. And remember for the exam that you should always relate your interpretations to the context of the question, like I said. So rather than saying you're 95% confident that the interval contains the true mean, you would say we are 95% confident that this interval contains the true mean systolic blood pressure for Thai men aged 50 to 60 years. The second question asked, what is our margin of error? Our margin of error is already calculated for our confidence interval formula. It's what we add and subtract from our sample mean. So this is 2.98. And this margin of error measures the accuracy of our sample estimate of the true mean. And it tells us the maximum amount by which the sample mean results are expected to differ from those of the actual population. And our final question was, what can we do to decrease the margin of error? We talked about this a couple of tutorials ago, but the margin of error is dependent on three things: the T we use, so the level of confidence, the sample standard deviation, and the sample size. So if we wanted to decrease the margin of error, we can do three things. We can use a smaller value of T, so less confidence. We can reduce the sample standard deviation, or we can increase the sample size. But decreasing the level of confidence isn't a good option because we'll be less confident that our interval contains the true mean. And decreasing the sample standard deviation is pretty much impossible. So the sample size is the thing that we have the most control over. So the main thing we can do to decrease our margin of error and decrease our confidence intervals is to increase our sample size. So you're given the following information. The null hypothesis is that the true mean equals 117. The alternative hypothesis is that the true mean is greater than 117. Our sample mean is 60, our population standard deviation is 42, our alpha level is 5%, the effect size is 4. What is the power of this test? So the first step is to find the critical value. So in order to reject the null hypothesis, we need a Z-score of what? So since our alpha is set at 5% and we're doing a one-sided test, we know that with a p-value of 0.05, we'll get a Z of 1.645. We then convert this Z-score back into our study units to find our critical value. So the rejection region tells us the value we need in units from our study to reject the null hypothesis. We use our Z formula to solve for our sample mean that we need to reject the null hypothesis. And we find that we need a sample mean of 125.92 to reject a null hypothesis. With the critical value, we calculate our Z beta. So our observed score is 121, calculated by adding our effect size of 4 to our population mean of 117. We subtract this observed score from our critical value of 125.92 and divide by our standard error. So our formula is our critical value minus our observed value divided by the standard error. And this gives us a Z beta of 0.91. And the next step is to find the corresponding probability for the Z score. So we can look in our Z table and we find that this is 0.181. Now, last week when I was just introducing the concept of power, I mentioned that the next step is to subtract this probability from 1. But there's actually a little bit more nuance to this. we subtract this value of 0.181 from 1 only if our observed score is more extreme or further away from the hypothesized mean than our critical value. In this case, our observed score of 121 is less extreme or is closer to the hypothesized value of 117 than our critical value of 125.92. So in this case, the value of 0.181 is actually equal to our power. So in other words, our power is 18.1%. So this makes a lot of sense if you draw it out, and you can see that the area under the red curve that corresponds to power, so 1 minus beta to the right of the critical value, is less than 50%. So it makes sense that this would be 18.1% here. So let's say we're instead interested in the power to detect a larger difference of 10 rather than 4. So everything else is the same except for our effect size, which has gotten bigger. So what is the power of this test? Our critical value stays the same. Our observed score is now 127, calculated by adding our effect size of 10 to our population mean of 117. And we can see that our red curve, where the alternative hypothesis is true, has shifted to the right, and our observed score is now further away from the hypothesized mean of 117 than our critical value of 125.92. So in this case, we know that our power is going to be greater than 50% just by looking at the area under the curve. So we proceed to subtract our observed score of 127 from our critical value of 125.92, and we divide by our standard error, and this gives us a Z beta of negative 0.19. And the next step is to find the corresponding probability for this Z score. So we look in our Z score and find that this is 0.4247. Since power equals 1 minus beta, our power is 1 minus 0.4247, which gives us a power of 0.5753. So our power is about 57.5%. So again, this makes sense if you look at our graph as the area for power, or 1 minus beta, to the right of the critical value under the red curve, or the distribution where the alternative hypothesis is true, is more than 50%. So just to summarize, when our observed score is more extreme or further away from the hypothesized mean than the critical value, then we subtract the probability associated with Z beta from 1. If our observed value is closer to the hypothesized mean than our critical value, we do not subtract this from 1. I know that this sounds a little complicated, but it should make sense as you practice it a bit more. And I'll also upload a document to Connect that shows this comparison of effect sizes using an example from last week's tutorial. Okay, so just a couple of more conceptual practice questions. The first is, what is the difference between a standard error and a sample standard deviation? So a standard deviation is the average distance between individual observations or raw scores and the mean of a sample. So this tells you how much individual observations vary from the mean. So for example, if we had a group of people and calculated their ages, the standard deviation would tell you the average distance from the individual ages and the mean age of that sample. On the other hand, the standard error tells us the average distance between a sample mean and the population mean. So this quantifies how precisely you know the true mean of the population. It takes into consideration both the value of the standard deviation and the sample size, and it decreases as sample size increases. The next question is, what is the difference between a distribution of a sample and a sampling distribution? So with the distribution of a sample, the unit is an individual observation. So for example, let's say we take a sample of 50 people and take their heights. Those individual heights are the units. The mean is defined by x bar, the sample mean, and this would be the average height in our sample. The standard deviation of our sample is defined as the average deviation of individual observations from the mean. And as our sample size gets larger, our sample estimates get closer and closer to the true values or population values. And this does not mean that this will follow a normal distribution. If a population is really skewed and we take a sample from that population, we are likely going to have a skewed distribution as well. In contrast, with a sampling distribution, our unit is the mean of each sample. So if we took 1,000 samples of 50 people and calculated the mean height of each of those samples. So we expect to get a sample mean that equals the true mean, but know that our sample mean will vary from this a bit. And it'll vary from that expectation with a standard deviation of the true standard deviation divided by the square root of the sample size. And this is sometimes referred to as the standard error, but as I've mentioned, this has a slightly different meaning than the standard deviation of the sample mean. So essentially, the standard error is used to describe the accuracy of a sample mean as an estimate of the population mean. It relies only on the information we have as part of our sample, and is used when we do not know the true population parameters, which is most often the case. On the other hand, with the standard deviation of the sample mean, you do know the true population parameters. So in other words, the standard error gives you an estimate of how close your sample mean is to the population mean. The standard error is computed solely from sample attributes. So we're using this sample as a representation of the population. So using the information from our sample to estimate this population parameter. The standard deviation of the sample mean shows you how much your sample mean differs from what you know the population mean to be. The standard deviation of the sample mean cannot be computed solely from sample attributes. It requires knowledge of one or more population parameters. So for example, the population mean. And with the sampling distribution of the mean, as our sample size gets larger, the sample mean will approximately follow a normal distribution. So that's it for this tutorial. In the next tutorial, we'll introduce the paired t-test, the two-sample t-test, and the non-parametric alternatives for these tests.